This is relative entropy introduced by Ludwig Boltzmann in 1878 in physics and reintroduced a century later by Kullback and Leibler in statistics and information theory, where it is called the Kullback-Leibler divergence. This simple equation turns out to be fundamental in estimating the parameters of machine learning models. In this video, I will start with basic fundamental concepts and walk you step by step all the way to the point where I show you how to use Python programming language and some of its libraries to estimate the parameters of linear regression in machine learning. Since this video is part of a series on machine learning from the lens of physics, before getting into the main subject, let me summarize the following two videos. If you have watched them already and remember the details, you can skip to the next chapter. In this video, we discussed that by God equation in machine learning and physics, I am referring to a general form for the probability function governing the occurrence of events in a system. The equation provides a universal framework for deriving different machine learning as well as physics models based on the shape of the probability function. In terms of a spreadsheet of data, it determines the probability of observing specific values for the columns of the spreadsheet, in other words, the variables of the system. Next, we showed that because of the maximum entropy principle, which has the same mathematical form in physics and information theory, most of the time we can ignore higher order terms in the Taylor series of this F, which we call the effective free energy of the system and is closely related to the surprise in statistics. We showed that after rearranging the terms in the Taylor series, we can write it in the form of a Gaussian distribution for the target variable, the variable that we would like to predict. We also discussed that this equation implies machine learning's linear regression. And today, we would like to derive the linear regression equation more rigorously and also present a way to estimate the parameters of this distribution, as well as the parameters of the linear regression using data. So let's get started. First, let's inspect f in the probability function. It has a different name in different fields. In statistics and information theory, this is the surprise shifted by a constant. In particle physics, this is called the action. And in statistical mechanics, it is called the effective free energy. As a physicist, I prefer the name effective free energy since I am familiar with energy concepts. I won't be using the particle physics naming because in particle physics, the nature of probability is randomness. In the rest of the fields, the nature of the probability is mostly uncertainty. Now, what is the difference between uncertainty and randomness? Well, uncertainty comes from our ignorance. For example, when I throw a coin, we usually say the chance of a head is 50%. But in principle, I can measure all the forces that my hand applies to the coin and run a couple of physics equations to find out exactly if the result would be a head. However, since there are too many factors to take into account, a probabilistic description is the practical way to go. So in this case, the probability is due to uncertainty. But in particle physics, the probability is fundamentally built into the physics of the event. For example, when shooting a particle toward a wall with a double slit on it and observing the particle on a screen down the way, all of the observations suggest that the particle has passed through both of the slits simultaneously. In this case, probability has a different nature, randomness. In this video, I'm going to cover machine learning, where probability is mostly due to uncertainty, our ignorance. Hence, the name effective free energy for f is more suitable. Just like a ball in a bowl that moves toward the bottom of the bowl, where the gravitational potential energy is minimum, data in our spreadsheet tends to move toward the minimum of the effective free energy and stay there as the equilibrium state. That is how I would interpret the f in this equation. Let's now add the logarithm of the normalization factor to the f to construct an object that in statistics is called a surprise. It is equal to the negative of the probability. To see the reason for the naming, let's say I throw a coin. What is the chance for the coin to hit the ground? It is 100%. In other words, the probability is 1. And the logarithm of 1 is 0. So surprise is 0 for this case. In other words, when I throw the coin and it hits the ground, nothing is surprising here. Now if I throw the coin and it goes up and up and up, the probability is 0. And minus the logarithm of 0 is infinity. So there is an infinite surprise if I throw the coin and it goes up. Now we can define another concept called entropy, which turns out to be extremely fundamental in both physics and statistics. In both fields, entropy is defined by the following equation, which is the expected value of the surprise. The concept was first introduced by Boltzmann and then improved into the form that we just see on a screen by another physicist named Gibbs. Then a century later, the same equation was written down by Shannon in statistics. Anyways, entropy is a measure of disorder in the system. A bunch of particles all at one single location of a container have a very low entropy since they are very orderly located. But when the gas molecules are spread all over the container, entropy or disorder is much higher. In physics, the second law of thermodynamics, a holy law of physics, states that a system left on its own moves toward maximum entropy or disorder state. The same also exists in the information theory. For example, when I release a gas in one location of a container, it will spread out to maximize entropy, but we never see all the molecules get back to the original location and stay there. So this is the maximum entropy principle in action. Now, what does this mean in terms of the probability equation? It means the probability function, the distribution, evolves with time. The time evolution of the probability's shape will only stop when the system is at the maximum entropy state. That is why we call it the equilibrium state. In physics, since we know the underlying principles, we have some equipment to find out how the probability evolves with time. But in machine learning, in most cases, we have to wait for the system to reach the equilibrium before collecting data. And that data can predict the system as long as the system is not pushed out of the equilibrium state by an external factor. If you haven't seen this video, I recommend watching it. Here I explain that when the system hasn't reached the maximum entropy state, machine learning is meaningless, because by the time we are done collecting data, the probability function that governs our data spreadsheet has evolved into a different form. In that video, I showed how to find out if the system has reached an equilibrium or if it is still evolving. Now, we never know the true form of the probability function. But assuming that the system is in the equilibrium state, and therefore at the minimum of the effective free energy, we can ignore the higher order terms in the Taylor series of f and end up with this form. In this equation, we show the target variable that we want to predict by y and the rest of the variables by x1, x2, etc. And the rest are constants that we would like to estimate using data. For this purpose, we need to somehow measure how far away the estimated distribution is from the true distribution. Here comes the concept of relative entropy, first introduced by Ludwig Boltzmann. The title of Boltzmann's article, originally in German, using Google Translate reads, "Further remarks on some problem of the mechanical theory of heat." This relative entropy was reintroduced a century later in statistics and information theory, where it is known as Kullback-Leibler divergence. As the name suggests, it measures the divergence, the difference, of two probability distributions. Let's now refer to the true probability distribution by P and our estimate for the probability distribution by G. Then the relative entropy is a measure of the amount of information we lose if instead of the true distribution, we use the estimated distribution. It is defined as the expected value of the difference between the surprise in the true distribution and the surprise in the estimated distribution. As a sanity check, let's assume that our estimate distribution is perfect, which means G and P are equal. Then the relative entropy is 0, which means we haven't lost any information in our estimation. Now the question is, we never know the true distribution to insert into this equation. How can we use this relative entropy in practice? The answer is that we use data to find a non-parametric estimate for the true distribution and insert that into the equation. How do we know that data provides a good estimate, although non-parametric, for the true distribution? There is something called the law of large numbers. It states that the empirical distribution that we infer from data converges to the true distribution when the data size is infinity. In other words, the more data I collect, the better estimate of true distribution I will have. Let's now separate the terms in relative entropy into two parts. One term contains our estimated distribution and therefore has the unknown parameters that we would like to estimate, and the other term doesn't have our estimated distribution and therefore has no parameter that we would like to estimate. Now we use the empirical distribution in place of the true distribution, and here is our estimation of the relative entropy. In this equation, the sum is over data samples. In other words, the index I refers to a row in my data spreadsheet. So I looped over the rows of the spreadsheet, computed the term for each row, and then sum all of them. Let me remind you that this relative entropy is a measure of the information we lose if instead of true distribution, we use our estimated distribution. That means we would like to minimize this information loss. So we must tweak the unknown parameters of our estimated distribution such that the information loss is minimal. Note that the second term in the relative entropy does not contain any of the unknown parameters of our estimated distribution. I can only minimize the contribution from the first term. That means we can only minimize this term by varying the unknown parameters. Now I use a trick. To minimize a function, I can maximize the negative of that function. To see why this works, look at this plot. I have plotted a function that has a minimum at x equal to 0. I also have plotted the negative of that function. As you can see, the minimum and maximum of the two plots are both at x equal to 0. Let's now multiply the negative of the function by 2. Still, the maximum is at the same location. This tells me that even if I multiply the negative of the function by a number such as the number of rows in my spreadsheet, the maximum stays at the same location as the minimum of the original function. Getting back to minimizing the information loss, I can therefore maximize the like term to achieve my goal of reducing the information loss. Remember that the sum of a bunch of like terms is equal to the log of the multiplication of those terms. Let's therefore rewrite the like term into this form. In statistics, the argument of this log is called the likelihood. Therefore, the term I'm going to maximize is the logarithm of the likelihood. Let's recap. I would like to maximize the likelihood by changing the following unknown parameters, which happen to be the constants of Taylor series of the effective free energy in the God equation. And our estimated probability distribution has the following form. To find the optimal values for these parameters, I need to take a derivative of the likelihood with respect to every single one of them, and then set all those derivatives to 0, and then solve the resulting equations. For most of distributions, there is no analytic solution to the resulting equations, and we need to use numeric methods to search for the maximum of the likelihood. There are many algorithms for this purpose, like gradient descent, or in this case, gradient ascent. The good news is that most of these numeric methods are implemented in Python libraries and can be used conveniently by a line of code. For this particular case, in which we have neglected all the higher order terms in the Taylor series of effective free energy, there are analytic solutions. You can find the details of the derivation of the analytic solutions in most textbooks. So I will skip the process and only present the results. Here the first equation coming out of the maximization process is the linear regression in machine learning. It states that the mean of the variable that I would like to predict, the mean of y, is equal to a bunch of constants multiplied by the rest of the variables or the columns in my spreadsheet. The second equation tells us that the optimal value for sigma square is the empirical variance of the target variable. It provides a practical way to compute the parameter using our spreadsheet. In this equation, the index I refers to each row of our spreadsheet, and yi refers to the value of y in that row of the spreadsheet. And y bar is the average of all the values of y in that column. And n is the total number of rows of the spreadsheet. The next equation is the normalization factor of the God equation. It expresses the normalization factor in terms of the variance, the sigma square, that we already estimated using data in our spreadsheet. And finally, the last equation provides an estimate for the beta coefficients. But instead of writing the analytic solution, I wrote another minimization equation that appears in the middle of the process. I wanted to introduce another concept in statistics and machine learning. Starting from maximizing likelihood and taking a few straightforward calculations, we arrive at this minimization task. Here what we need to minimize is called RSS, which stands for the Residual Sum of Squares. This minimization has an analytic solution as well, but since I'm going to show you how to use numeric methods to find the estimations, let me instead talk about the interpretation of this equation, which is important in machine learning. For a given set of beta values, this equation is a straight line relating the target variable y, the column in my spreadsheet that I would like to predict, with the predictor variables, the rest of the variables in my spreadsheet. For example, if I only have one predictor, and I select beta 0 to be, for example, equal to 2, and beta 1 to be equal to 0.5, then I can plot the right-hand side of the equation. Let's also draw the two values of y in the spreadsheet that I'm going to use to train the model. The minimization equation then states that the sum over the square of the distances between the line and the two y values must be minimal. That means I need to keep changing the values of beta until I find a set of beta values that minimizes the sum over the squares of the distances. In the last chapter of this video, I'm going to show you how to practically find the base parameter of the linear regression and also the probability distribution by a few lines of code in Python programming language. Let's assume I have collected some data and stored them in this spreadsheet and want to use it to train a linear regression. In this spreadsheet, I have two features, predictor columns, and one target variable. I also have 400 rows in the spreadsheet, which are the data samples. First thing, I save this spreadsheet in a file with a CSV format because it's easier to read it in the code. Next, I open a Python Jupyter notebook and import the pandas library and arbitrarily give it the name PD. I also import the NumPy library and give it the name NP. And also import linear regression from the scikit-learn library. Now I read the spreadsheet and store it into the variable df, which stands for data frame. Now I define the target and the feature variables. Here y holds the target column of my spreadsheet and x holds the rest of the columns of the spreadsheet. To find the y bar, I will use the mean function of NumPy. To find the sigma square, which we discussed would be equal to the empirical variance of y, I use the variance function of NumPy. To find the beta parameters of the linear regression, I will train a linear regression model using the x and y variables of my spreadsheet. The optimal parameters that maximize likelihood, which minimize the residual sum of squares, are stored in this variable of the model. Let me also mention that there are some other concepts like split and test, hyperparameter search, and many more that I will discuss in future videos. Lastly, let me introduce a free service from my consulting and coaching company, CompuFlair. If you need the source code of this video and other videos and also need help better understanding them or customizing them, simply log into our website and ask our chatbot to give you the source code of this video by searching something like I need the source code for linear regression in CompuFiller's machine learning tutorial series. The chatbot will return a bunch of pipelines with their IDs. These pipelines are all human written and free of AI hallucination. Select the pipeline of this video to go to another page in which the source code that I presented in the video is returned. In addition to the source code, we have also added enough hidden instructions for the chatbot to be able to help you to get the answer to your questions. These pipeline-specific hidden instructions written by our team will reduce AI hallucination and help the chatbot to better serve you. Also, if you are interested in our data science coaching or consulting services, please navigate to the solution page and fill out the form. I hope you have enjoyed this video. Take care, and I'll see you in the next videos.